Okay, so good morning, good afternoon, or good evening to you all who are watching these lectures. They will be recorded and online for you only, and we'll hold some open office hours using Google Meet. I'll email you all for that, so that if you want to come to me with questions about this lecture or other ones, you can do so. Right, so what we have are 6 hours of nuclear physics left to teach, and they would normally take place in person, but they will all be recorded for you now. I'm hoping this format works quite well. You should be able to see the slides as well as myself, and when I need to go through some examples, I will share another window, and you should be able to see that too. But please do get into touch if you have any comments or suggestions or questions on how this is working. So our first nuclear lecture is going to be on the basic nuclear properties, and then we'll start having a look at radioactive decay and fission and fusion. Right, so what we will do in this hour is to have a look at why we study this, by this I mean the strong nuclear force. We'll have a look at the different types of nuclei that we can have. In particular, we're interested in the stable ones. We'll have a look at how we model the binding energy and the mass of nuclei and other properties such as their spin and their parity and their size, and of course, their nuclear moments. So nuclear physics, even though it's just the last 6 lectures of this course, is actually very, very, very important. Um, it plays a very fundamental role in our world, not just what we're made up of and the properties of atoms and things like that, but also over much longer timescales, the stars, how they were formed and their lifetimes, how even the chemical elements that we're made up of were even made. And these processes, particularly nuclear synthesis, are very important to understand the origin of the universe. Now, practically speaking, there are many applications of such nuclear physics. We don't have a big nuclear physics program at Cambridge. It's mostly in the engineering department, but there are many, many jobs, for example, in this area that might use radioactivity in health, for example, in radioactive dating or NMR, or to study materials with NMR again, and even in nuclear power and I guess more traditionally weapons as well. But nuclear power particularly has quite a big focus in terms of our energy needs recently, and I'm sure some of you will end up going into that industry. So let's have a look. What are we talking about for the nuclear force? Um, so previously we've been looking at particle physics, where we've been looking at the fundamental force, the nuclear force, on very, very tiny rain, yeah, length scales. Now, if two protons interact, if we have a look at this diagram here at the hadron level, if two protons scatter off of one another but do not break up, it means that they have passed between them a colorless particle, and this is actually the pion. If you remember when we had a look at the strong nuclear force when we were discussing the Yukawa potential, this is essentially um, what is going on. If they pass a gluon between them, it means there's some color exchange and the protons are no longer overall colorless. So if protons or neutrons as well, this goes for protons and neutrons, if they remain they're composite particles and they don't break up, it means they're exchanging colorless states between them. And that exchange initiates a force between them and binds them together. So on a very complex quark level diagram here, the quarks inside of our protons are exchanging gluons, which results in a state like an up or anti-up bound state, like a pion, being exchanged between the two. And you can see how complex this is. It takes pretty much all of our quarks here are taking place in this interaction. It's a many body problem. We need to take into account all of those quarks in each of those protons that we're looking at there. But in nuclei, we've got many different protons and many different neutrons. So this is a very, very complicated problem. And the quarks inside the protons and neutrons don't behave in one way or the other. So they don't behave like they're completely independent of one another, but nor do they behave as if they were completely bound. And this makes it very difficult for us to calculate the strong nuclear force at the quark level and at this sort of fundamental physics level. What we are going to do as part of this course is have a look at what we can deduce empirically from data, what we can essentially model, but this we won't be looking at the strong nuclear force from the very first principles because it is so complex, because it is so difficult. Maybe something, again, it's this one of the many areas which needs work, and maybe this is something that if you end up going into research, this will be something that you can contribute to. So let's start off. We'll be discussing the stable nuclei in this this course. So it's a little bit of a misnomer here because we will be talking about decaying particles. Now, when I talk about stable particles, it's particles that aren't going to decay via the strong interaction. If they decay via the strong interaction, that happens on a very, very, very short time scale. And so they are not considered stable. But stable nuclei can be considered those that decay via the weak decay, either the electromagnetic or the weak decay, so via beta emission, alpha emission, or photon emission as well. And this can happen over much longer lifetimes. But we're talking about very tiny fractions of seconds, but they are considered stable. Now, if we have a look at these stable nuclei, we can plot these with their number of protons here on the x-axis and the number of neutrons here on the y-axis. And these data points here are all of our stable nuclei. And there is a trend here when they're very light for them to have equal numbers of protons and neutrons. But as they get heavier, the number of neutrons or the fraction of the nuclear weight from neutrons appears to increase. They become sort of neutron enriched. We also find that most of these have even numbers of neutrons sometimes and protons as well. So they tend to form, the protons and neutrons tend to form pairs. In fact, out of all of these, there's almost 300 of them, only 8 of them actually have odd number of neutrons and an odd number of protons. And there's a few of these stable nuclei here that seem to exhibit quite a large number of isotopes and isotones. There's something special about them that seems to produce lots of slightly different versions of very stable particles. Next, what I'd like to discuss is binding energy. So let's try and get this to fit better. Hit the page. Okay, is the binding energy. There we go, that's better. Right, so how can we describe the mass of a nucleus, i.e. all of its protons and its neutrons, but also the energy that it takes to actually be bound together? So we can describe the mass of any nucleus as being the mass of all of our protons and the mass of all of our neutrons and subtracting this binding energy. And this is a really important quantity because this gives us information about how our protons and neutrons are actually bound together, that strong nuclear force. It also tells us how stable a nucleus is, and also if energy is going to be released or needs to be put into some reaction that we're going to look at. To understand this binding energy from first principles is extremely difficult because it's difficult from first principles to understand the strong nuclear force because it's a many-body problem. But we can come at it from another angle. If we very accurately measure the mass of all of these nuclei via mass spectrometry, we can then calculate this binding energy and understand then how the force between these nucleons is working. Just a little aside, we don't use it so much in this course, but you'll find in textbooks quite a lot the separation energy is discussed of a nucleon. And this is the energy that is needed instead to split. So the binding energy is the energy that's needed to split a nucleus up into all of its constituent protons and neutrons, and telling you about how all of them are bound together. The separation energy is just the energy that's needed for a single nucleon to be removed from the nucleus, which is of course much less. So we'll be concentrating on the binding energy here, but these two things of course are related. Now let's have a look at this binding energy. What we're going to do is discuss the binding energy per nucleon so that we're putting everything on more equal footing. So this is what's plotted on the y-axis here, the binding energy per nucleon, because of course for those very larger nuclei, you're going to have far more nucleons actually bound together, and the overall binding energy will be larger. So let's normalize it to the number of nucleons inside that nucleus. So it seems to, for hydrogen down here, be very, very low and increase to this very broad maximum, actually. As you get to sort of nuclei with 20 protons and neutrons, we seem to have this very broad maximum here at about 8 MeV per nucleon. And that's quite large. That's really quite large. If you compare this to the binding energy of electrons to atoms, that's very small at about 3 keV per nucleon. So this is much, much larger, 3 orders of magnitude larger. Now, the fact that we've got a broad maximum here for most of our nuclei implies that we actually have a, a saturated force, that nucleons are only actually interacting with their neighbors and not with all of the rest of them. Otherwise, it would be growing with the number of nucleons in the nucleus. So it appears to be short range and it appears to be saturated. So our proton or our neutron inside a nucleus is only interacting with its neighbors. We've also got a couple of peaks here. I hope you can see the mouse that I'm hovering over. There seems to be quite a large binding energy for helium here before it goes back down for lithium and then continues to climb. We also have a peak for carbon-12 and oxygen-16. And the peaks for the others are a little bit less easy to see. Now, these peaks appear to happen for nuclei that have some number of 4 times 4. So we've got, for example, 4 nucleons in helium-4. We've got 3 times 4 nucleons in carbon-12 and 4 times 4 nucleons in oxygen-16. There appears to be a particularly stable, i.e. high binding energy, if you've got some number of alpha particles, so a bound state of 2 protons and 2 neutrons. So these are called alpha stability peaks. They show a very high binding energy when you've got that configuration. And finally, the last thing I'd like to point out about this plot is that there's a rough maximum at 60 nucleons here. It rises, the binding energy per nucleon rises to about 60. So this is a very tightly bound state around iron here, and then tends to drop off very slightly for the more heavy ones. So that means that to the right of this this sort of broad maximum, we are going to have fission. These nuclei actually split up into lighter nuclei to try and increase their binding energy. Whereas for fusion, the lighter nuclei will try and bind together into heavier nuclei as well to increase their binding energy per nucleon. So it defines when fusion and when fission will happen naturally. Well, next, let's have a look at the nuclear mass. This is really quite interesting to try and have a look at. As I said, it depends if you want to discuss the atomic mass or the nuclear mass. But for example, the nuclear mass is going to be the number of protons that you have, the number of neutrons that you have multiplied by their masses, and then subtracting this binding energy. If you want to take into account the atomic mass as well, you need to account for those very small electron masses. So what we're going to do is we're going to take a very simple approach and model our nucleus as a drop of liquid so that we have something with a uniform density throughout the drop, and that density drops to zero at the surface. So this is really good. In a drop of liquid, we've got very short range intermolecular forces holding that drop together, and this is going to model our short range nuclear force. The density is uniform throughout the drop, and it doesn't depend on the drop size. That will be uniform. And this is going to be very good for our nuclei as well, because then our density is independent of the nuclear size. And then finally, if you consider a drop of liquid, if you want to evaporate a small mass from that, it will require a fixed amount of heat to do that. And this is equivalent to our binding energy per nucleon being roughly constant as well. So let's have a look at this binding energy and how we can model it like a drop of liquid. We're going to start off with a volume term, that the strong force is going to bind our nucleons together, and for every nucleon that we add, for example, our strong force will increase, and this binding energy will increase. So every time we add a nucleon, so our number of nucleons is A, we're going to increase our binding energy. Since our number of nucleons is proportional to the volume, then this is called our volume term. So we're going to have some constant times the number of nucleons that we have to describe the overall binding energy here. The next thing that we should consider is that the nucleons on the surface of our drop or our nucleus are going to have fewer neighbors and thus be bound less tightly. This is going to decrease the overall binding energy. So since we said the volume is proportional to the number of nucleons A, then our radius is proportional to the cube root of our number of nucleons. Thus, our surface area, the nucleons on the surface area, that's the important thing, is proportional to the radius squared, thus the number of nucleons to the power of 2/3. So we're going to decrease our binding energy here by some coefficient here, AS, multiplied by the number of nucleons we have to the power of 2/3. It's going to bring it down. And finally, we've got to account for the fact that we have protons and neutrons in our nucleus, in our drop, but the protons are going to repel each other, of course, because they're like charge. So we're going to add another term here that is going to decrease our binding energy. It's going to depend on the number of protons that we have, z squared, and also depends on the range over which they are interacting. So it depends on the radius, 1 over the radius here. And we've just said that the radius is proportional to the number of nucleons that we have cube rooted. So this is a very simple approach, treating our nucleus like a liquid drop, that we have an overall strong force for the volume, subtracting effects for the loosely bound surface nucleons, and also the fact that the protons are going to repel each other. We can't stop there though, because this is a very, very simple model. Now, like I said a few slides ago, we find that we usually have equal numbers of neutrons and protons, particularly for the light nuclei. This doesn't account for any of that. We also haven't accounted for the fact that the protons and neutrons quite like to come in pairs. And why is that favored? So what we're going to do next is add a little more complexity to this liquid drop model. What we're going to do here is treat our nucleus actually as a Fermi gas. So that now we're going to assume that our protons and neutrons can only assume particular energies, and that will be in accordance with our Pauli's exclusion principle. And this is going to allow us to address those two problems, that nuclei tend to have equal numbers of protons and neutrons, and that those protons and neutrons appear to prefer to pair up. So we're going to have another term for our binding energy, which is going to decrease the binding energy here. And we're going to have some coefficient again, this A, this time sub-A because it's the asymmetry term. And it's going to account for the protons and neutrons. If the larger the difference between the protons and neutrons, the larger this subtraction term is going to be. Now, you can have a look at this on problem sheet 4, where you get to basically have a look at this asymmetry term. If you model our protons and neutrons like a Fermi gas, you'll find that you can minimize the kinetic energy of our protons and neutrons if we have equal numbers. So the further away we are from equal numbers of protons and neutrons, the larger this asymmetry term is going to be and the smaller the binding energy. Now, this is quite an interesting correction to our binding energy because as you get to larger and larger nuclei, more numbers of higher A, essentially, our energy levels are actually more closely spaced, and this asymmetry term essentially gets scaled down. And finally, we're going to add a term to account for the fact that protons and neutrons like to pair up. So we have even numbers of protons and even numbers of neutrons. Now, this is simply empirical, what we're doing here. This isn't something like the other terms, which is taking into account some physics. We're going to add a term here. We call it delta. It's going to be adding something to the binding energy for even nuclei, for even numbers of neutrons, even number of protons. It's not going to do anything. It's going to be equal to 0 if we've got one even and one odd. And it's going to subtract something from the binding energy if we have an odd nucleus. So basically, this is going to try and account for the fact that neutrons or protons, pairs of them, actually favor when you've got their spins pointing in opposite directions, i.e. when they've paired up. And this gives us a symmetric spatial wave function, and it's going to give us a lower overall energy state. So when we've got the pairs of spins, one up, one down, we actually have a symmetric spatial wave function, and we have minimized our energy overall. So we're adding something here to increase the binding energy if it's an even nucleus, and subtracting something if it's odd. So let's try and summarize this here on slide 11. We're going to put all these terms together. So as I said, we're starting off with some volume term here that gives us a overall average binding energy per nucleon. We are then going to subtract something to take into account that the surface nucleons are less tightly bound. This is the surface energy, and it's going to decrease the binding energy per nucleon. And because the very low mass nuclei down here have a larger surface area to volume ratio, then this makes a more significant difference here. Then we're going to subtract a term for the Coulomb energy, this part in yellow here, and that's going to have a larger impact on the higher mass nuclei because they have more protons. And then we're going to subtract a part for the asymmetry energy, i.e. how far away they are from even numbers of protons and neutrons. So here we have our semi-empirical mass formula here. This is something that's very important for the nuclear part of the course that enables us to understand how the nuclei are bound together to give the mass that we measure. It depends on the number of protons that we have here, the number of neutrons that we have here, and the binding energy, which depends on the volume term here, the surface term, the Coulomb term, the asymmetry term, and the pairing term. So as I said, this isn't something that we're doing from the very first principles. This is something that we're going to try and understand from data. It's a many body problem, and this binding energy is very difficult to calculate from first principles. But we can measure the mass of nuclei using mass spectrometry. So when we do that, we can obtain the binding energy for all of these different nuclei and do a fit to this data and obtain these coefficients for the volume, surface, Coulomb, asymmetry term here, and also the pairing term. And so this is what we've done. These coefficients are given here. This is the fit to data that we get, and these are given in MeV. Right, so next I'd like to discuss nuclear spin. So a nucleus is an isolated system of protons and neutrons, and it's going to have a very well-defined spin. Simply put, we've got the sum of all of our protons and neutrons, those individual nucleons, and they're going to contribute to the total angular momentum here. So we're going to sum up the total angular momentum for each of our protons and neutrons, and each of these are going to be sitting in a particular L state and have a particular spin. Right, so what we need to understand is that the spin of these protons and neutrons is always going to be a half. They are fermions, so that's pretty easy. And then the orbital angular momentum, now that's definitely an integer, we know that. And it's so, how do we understand what the orbital angular momentum then, sorry, the overall spin of our nucleus is, depends on the, 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 the protons and neutrons that we have. So if we have an even number of protons and neutrons, we know that this total spin is going to have to be an integer, because our total spin here will also be an integer and our orbital angular momentum will be an integer. If we've got an odd number of nucleons, then this is going to be a half integer, because this is always an integer and that's a half integer. And what we find as a special case here, actually, which you're going to have to try and remember, is that if we have a nucleus with an even number of neutrons and an even number of protons, what we so-called an even nucleus, they always have a total spin of 0. So there's a special case there. Always have um, even nuclei have a spin of 0. Total number of nucleons is even. We're going to have an even spin. Odd, we're going to have a half integer spin. So let's have a look at parity, and we've studied parity a lot in the nuclear part of the course. Now, the parity of our nuclei are really no different. We're going to label our, we're going to use the same notation as we did for the nuclear particle part of the course, where we've got the spin parity of a particle, for example, spin 0 even parity, or here spin 2 odd parity. And we calculate the parity in the same way as we did for the nuclear, the particle part of the course, where we're having a look at all of the constituents of a state. So what we're going to do for the parity of a nucleus is have a look at the intrinsic parity of our protons and neutrons and multiply all of those together, and then multiply this by the extrinsic parity of the system. So what L state is our system sitting in? So we know our proton or neutron, because it's made up of 3 quarks, is going to have a parity overall of +1 multiplied by the L state that it's sitting in, -1 to the power of L. So if we're looking at a nucleus with an odd number of nucleons, its parity is actually going to be given by the state that that unpaired proton or neutron is sitting in. What L state is it sitting in? What's its spin as well? I'm going to have a look at this in the context of the nuclear shell model. Now, all of the processes that we're going to be having a look at, if they are the strong interaction. So parity is actually conserved in the nuclear processes that we look at, because this is the strong interaction. And we can actually have a look at the photon transitions between nuclear states. We can measure the photons that come out from those. We can measure the parity and the spin of those protons and extract the parity of nuclear states. So we'll be having a look at that later with gamma decay. Click on that. The next to final thing that we're interested in here is, what is the size of a nucleus? And this is something that we can use both the electromagnetic and the strong interactions for. So if we use the electromagnetic interaction, that will be the interaction between charged particles. So it's going to tell us where those charged particles, where the protons are inside the nucleus. So we can scatter electrons off of nuclei, or we can have a look in I'll have a look in a minute, or we can have a look at muonic atoms, i.e. where muons are orbiting nuclei. And that's really interesting because the orbits of the muons are really quite different to when electrons orbit nuclei. And we can also have a look at mirror nuclei, and this is where we have um, the same number of nucleons between two nuclei, but different numbers of protons and neutrons. And beta decay between these nuclei are very important. Finally, we can use the strong interaction, and this is going to tell us where all the protons and neutrons are sitting. So we can also use the strong interaction to tell us where the matter is sitting inside of the nucleus. So it's going to tell us where the protons and the neutrons are sitting. And this is actually a little bit more complex because it's going to have to need to take into account the strong and the electromagnetic interactions at the same time. We can have a look at alpha particle scattering. That is basically a small nucleus of two protons and two neutrons, and they're going to interact with the other nucleus. And they're going to interact electromagnetically and via the strong interaction. We could have a look again, could scatter protons or neutrons off of nuclei as well. The same case there applies there, that it needs the strong force and the electromagnetic force. We can have a look at the lifetime of alpha particle emitters. We'll have a look at that as part of alpha decay, which is quite interesting. That tells us a lot about the size of nuclei as well. Or, for example, we can have a look at pi mesic X-rays as well. Now, we've got all of these different ways of having a look at the size of a nucleus, and it's very interesting that it doesn't matter if we use the charge or the strong interaction for the matter, we find that the radii are actually equal for all of these nuclei, for all of these different methods that we can use. They're giving equal radii for lots of different nuclei. So it doesn't matter if it's just the electromagnetic interaction or we have a look at matter as well, we find the same answer. So let's have a look at electron scattering. We scatter very high energy electrons off of protons. Now these do need to be very high energy. We want to have a look over very small distances of 1 femtometer here. So we're looking at exchanging photons of about 200 MeV. So we need very high energy electrons here. So this is simply the Coulomb potential. We know the Coulomb potential very well. We can pop that into the potential in the Born approximation for the differential cross-section. As a reminder, please go back to chapter 2 if you don't remember this. And when we do that, we obtain the formula for Rutherford scattering, which we know very, very well. Now, this Rutherford scattering here assumes that the proton is point-like, but it's not. The proton has a particular size. And it depends, this potential that the electron experiences depends on how the charge is actually distributed inside of the nucleus. So then let's have a look at this charge distribution and alter our potential that the electron sees. And this is going to depend on this difference in charge that it's going to see over the difference in the radius from the basic radius. So this small difference in radius will give a small difference in the charge that it sees and will tell us about how the charge is distributed inside of a nucleus. So this is very simply our typical standard Coulomb potential here, but we're going to convolute it with a normalized charge distribution. And we're going to call this rho here. So we can put in this convolution here as rho, and it should be normalized to the total charge of the nucleus. So let's pop this into the matrix element that we're going to put into the Born approximation for the cross-section. If we do this, we're going to get the matrix element that looks very familiar, this first part in red here, which is the typical Rutherford scattering off of a point-like particle. Then we've got this additional part here, which is called the form factor, and this is simply the Fourier transform of our normalized charge distribution. So our differential cross-section looks like our Rutherford scattering from a point-like particle, and then it's changed a little bit because of this form factor. So we can actually have a look at this form factor and do a simple calculation using spherical symmetry that allows us to extract the charge distribution as a function of this form factor. So if we measure this differential cross section here, we can find out our form factor and use this to get uh, our charge distribution. And that's what we're interested in. Where are the protons in the nucleus? And this will tell us the size of the nucleus. So we measure our differential cross section, we get our form factor, and then we have our charge distribution here that we're plotting on the y-axis, and then the radius of a nucleus as on the x-axis. So this is actually so our charge distribution is well modeled by this Fermi parameterization. We have pretty much um, a level charge distribution until we get to some particular radius where it starts to drop off. So this is a very good example of Fermi parameterization here. So we've got some um, just some standard charge distribution here before it drops off. And the way that it drops off is parameterized by two different parameters here. We've got the radius of the nucleus, and this is at the point where this row 0 here, the charge distribution at r equals 0, drops off to half of its value. Okay, so that's what we're defining as capital R there. And we find, and I'll show you in a minute, that this actually increases with the cube root of the number of nucleons. And we also have the skin thickness here, S, and this is telling us about how quickly it drops off, how quickly this charge distribution drops off. And we define this as when this nominal charge distribution here drops from 90 to 10% of that nominal central value. And this is really interesting. I'll show you on the next plot that this is the same for all nuclei. And this is telling us that the strong interaction drops off over the same range. And this is about 2.5 femtometers for all nuclei, this skin thickness, basically this gradient over which it drops away. And this is the range of the strong interaction. And this is telling you something quite fundamental about that range. So let's have a look at the data here for the charge density. So we've plotted this here for lots and lots of different nuclei here. There are some outliers here like hydrogen and helium, those very light nuclei. They're not quite fitting this, so I won't discuss that. But you can see that actually the charge distribution is roughly the same for all nuclei. It's hitting roughly about 1.2 times 10 to the 19 coulombs per centimeters cubed. They have roughly the same density of protons in all of these different nuclei that you can see here. And also their skin thicknesses, the drop off as the radius drops away, is all pretty much the same. These show almost the same parameterization here of about 2.5 femtometers, if you'd like to measure that for all of those. So we can infer then that we have some fixed radius here. So for example, we find that the radius is increasing with the number of nucleons, or the cube root of the number of nucleons here. And the fact that they've got the same charge density is telling us that this R0, that coefficient there, is about 1.2 femtometers. Try and remember that. That's something that's quite easy to plug into lots of calculations that you'll be making later. And this is consistent with a short range saturated force, as is that skin thickness. Now let's have a look at another method here. So we just did electron scattering. Let's have a look at muonic atoms. So electrons usually orbit nuclei, that's fine, but let's have a look at what happens when muons orbit nuclei instead. And this is quite interesting because they actually orbit much closer to the nucleus than electrons do, and they can be used to probe the nucleus because they actually end up interacting with the nucleus a little bit. So because the muon is 105 MeV compared to an electron, which is just half an MeV in mass, it's going to affect how it orbits. So if we have a look at the Bohr radius, that's proportional to 1 over the number of protons that you have and the mass of the particle that's orbiting. So these muons are much, much heavier. That means they're going to have a much, much smaller radius. If you compare hydrogen, for example, an electron will orbit that single proton at 53,000 femtometers, whereas a muon will orbit at 385 femtometers. So much, much closer. And if you consider lead, for example, because it's got a much higher charge for that nucleus, it's going to orbit even closer, actually at 3 femtometers there. And that's actually pretty much inside the nucleus. So we can use this to probe the nucleus. As the muon is orbiting sort of inside the nucleus, it's going to change the way it orbits. And we can see when and where it's changing. Now, the energy levels of the muon orbiting nuclei is also different because, again, it's far more massive. So the muon will rapidly undergo transitions to the lower energy levels, of course. Now, the muon isn't stable, but it's got plenty of time to do that. So the transitions will happen on the order of 10 to the minus 9 seconds, wherein its lifetime is about 2 microseconds. It's got plenty of time to do that. And you can see changes, for example, when we look at muonic lead, when it's interacting with the nucleus. For example, lead, where it's basically spending some time inside the nucleus. Bohr theory tells us that energy from the 2p transitions to the 1s transitions should be about 16 MeV. But because it's interacting with the nucleus, because it's inside the nucleus, this is about 6 MeV. So all of these changes can tell us about the nuclear radius. And finally, I'd like to talk about mirror nuclei. So this is where you have the same number of nucleons, so protons plus neutrons, but differing numbers of protons and neutrons. So take boron 11 versus carbon 11. Boron has 5 protons and 5 protons and 6 neutrons, whereas carbon has 6 protons and 5 neutrons. So if we have a look at our semi-empirical mass formula, there are slight changes in the mass, not only from the small differences between protons and neutrons here, but also in the Coulomb term for the binding energy. Because the carbon here has 6 protons, it's going to have a smaller binding energy because those protons are repulsing each other. So if you're going to look at the atomic mass differences or the nuclear mass differences, be careful whether you remember the electrons or not. So if we were going to do atomic mass spectrometry on these, we need to include the difference in the electrons. So the carbon is going to have 6 electrons and the boron 5. So if you have a look at the mass differences between carbon and boron here, this should be equal to your differences in the protons and neutrons. That tiny difference there. Carbon also has an additional electron, and also this small difference in the Coulomb term. So we can measure the atomic mass difference, and we can have a look at how carbon 11 decays to boron 11 via beta decay. And the energy of that positron here that it's taking, if we measure the energy of that positron here, it's going to tell us about how much energy is released in that decay and tell us about this Coulomb energy here. So we measure the beta decay between carbon to boron 11. And we can find the end point in that positron energy here as the total energy released into decay, i.e. when all of the energy has gone to the positron rather than the neutrino, and relate that to the difference in the Coulomb energy. And that depends, because it depends on 1 over the cube root of the number of nucleons, that's proportional to the radius there. So we can then measure this positron maximum energy, relate that to your proton, neutron, and electron masses here, and find the radius of these nuclei. And you've got a question about this, question 31, in your problem sheet to have a look at. Finally, what I'd like to discuss is nuclear shape. So, are nuclei spheres, or are they squashed or stretched in particular? Are they spheroids? Or, for example, are they even pear-shaped? Some of them are pear-shaped. It's quite interesting. And we can deduce this from their electromagnetic moments. Now, by measuring these nuclear moments, we can tell how the magnetic moments and the charge are distributed throughout their nucleus. And we'll have a look at these now, but we've got to have a look at the electric quadrupole moment and the magnetic dipole moment. So let's have a look at the electric moments. And this is interesting for how the charge, i.e. the protons, are distributed inside the nucleus. So similar to how we did for the electron scattering, we have nuclei that are not point-like particles, and we're going to have some distribution. So we're going to take our Coulomb potential and have some charge distribution that will normalize to the total charge of the nucleus. So you can do a multiple expansion of this. The details are in the small print here. And you will end up with a potential with different terms in R here, depending on the total charge here, and this small deviation in R, which is R dashed. So let's have a look at our potential now. Now, as I said, the overall charge distribution has to be normalized to the total charge of our nucleus. That's not going to change. And we can have a look at each successive power of 1 over r here. This first one in blue is the overall charge of our nucleus. And this doesn't give us any shape information at all. So it's not very interesting here, this E1 moment, sorry, E0 moment. Then if we have a look at the first power of 1 over r, this E1 moment, the electric dipole moment, this, because we have definite parity of a nucleus, it either has plus or minus 1, this is actually always 0. So again, it's not very interesting. The first interesting moment that we actually get to is the E2 moment, the quadrupole moment. And this is the one that's going to give us the information about the shape of a nucleus. So let's have a look at this. So I'm going to call this part here, this electric quadrupole moment Q. And it's going to depend basically on how it's stretched along an axis that we'll call Z. How its radius is basically stretched, and it's going to tell us about the charge distribution. Now, if we have a sphere, if we have a fully symmetric, fully spherically symmetric potential, then Q is going to be 0. Our quadrupole moment will be 0. Now, we find that all of our spin 0 nuclei have Q equals 0. All of our even nuclei have 0 quadrupole moments. They are spheres. But we have quite a few cases where we have quite deformed nuclei. For example, and try and remember this, sodium is famously very, very deformed. It's depends on which way you defined your z-axis, but it is very, very deformed. It's very, very egg-shaped, and it has quite a high quadrupole moment. And we find that because it's very, very, very deformed, we can't then model it very well as a spherical drop with some Fermi gas, and our semi-empirical mass formula tends to break down for these very deformed nuclei. So it's telling us when we have a very spherical nucleus and our semi-empirical mass formula works very well, or when we've got very deformed nuclei and we expect things to break down, like for sodium, for example. So we can have positive Q will tell us if it's a prolate spheroid, or negative Q if it's an oblate spheroid. And there's lots of cases actually that we're finding that this is an example for 2013 from the Isolde experiment in CERN, where we have quite a few now pear-shaped nuclei. For example, this is radium-224, and they have a non-zero quadrupole moment and non-zero octupole moments as well. So really making them non-spherically symmetric. The other moments that we're interested in are magnetic moments. So these magnetic dipole moments can arise from two different sources. The fact that we have magnetic dipole moments of the protons and neutrons inside our nuclei, these intrinsic magnetic dipole moments, because they have some spin, and also the fact that the protons can circulate throughout the nucleus. We have circulating currents which add to the magnetic dipole moment. So we can write down our nuclear magnetic dipole moment as something that's summing over all of the protons and neutrons, given their orbital states and also their spins. So this is our nuclear magneton again, this mu sub n, and it depends on our protons and neutrons here. Now we can simplify this somewhat by putting all of this sum here into Gj. This is going to be our nuclear G factor, and this is analogous to our Landau G factor in atoms. Times the nuclear magneton here multiplied by the total nuclear spin that we have. So that, like we said in the previous slide, if you've got an even nucleus with J equals 0, it's going to have a 0, its magnetic dipole moment will be 0 because it's a sphere. So we can actually predict GJ from the nuclear shell model. We'll have a look at this later to tell us about the shape of a nucleus. And we can also measure it using magnetic resonance as well, like is done for some of the experiments here. So we do have these very special cases for even nuclei that have J equals 0, and they have a magnetic dipole moment of 0, i.e. they are spheres. So finally, let's just summarize what we've discussed here. We know that the strong nuclear force is short range and it's saturated, and we can model this very nicely with the liquid drop model, plus some simple effects coming from the Fermi gas to bring us to the semi-empirical mass formula that give us the intrinsic masses of our protons and neutrons and the binding energy that tells us about the strong force, how the protons and neutrons are bound together. Please do become familiar with this. It's a very important equation. You have a volume term, a surface term, the fact that those surface nuclei have fewer neighbors and are less well bound, a Coulomb term to account for the fact that the protons are repelling each other, an asymmetry term. The further away we are from equal numbers of protons and neutrons, the lower the binding energy. And finally, a pairing term that favors equal numbers of protons and equal numbers of neutrons. We also had a look at the nuclear size, and there's lots of different ways of guessing this. Electron scattering, muonic atoms, mirror nuclei are really fun as well. And they're telling us that there's a constant density throughout all nuclei, and that the radius grows as the cube root of the number of nucleons. And finally, we had a look at the different moments that a nucleus can have, and it tells us about the shape of a nucleus. And also, we're interested in the spin and the parity, which we'll have a look at more throughout the rest of these lectures. Okay, so that's it for chapter 13. We'll have a look at the structure of nuclei next, and having a look at the nuclear shell model. See you then. Bye bye.